All right, hi everyone. My name is Anuj,
I'm Ravi.
and we're with the ACT program. We're going to be talking about the synthesis and modification of crown ethers for the detection of heavy metal cations in aqueous media. So, due to advanced industrialization throughout the world, we've seen a correlated increase in pollution of wastewater streams, and this is especially prevalent in poor regions throughout the world as they don't have the proper wastewater treatment systems to remove these metal cations. And this is of importance as heavy metal biomagnification can cause oxidative stress or the formation of reactive oxygen species or free oxygen radicals, which are highly unstable and can lead to cell lysis or death. And so, as you can see, we have a diagram of a wetland from China, and we can see that the amount of heavy metal cations can transfer over to irrigated agricultural land as this polluted water is used to water crops. And from there, these polluted crops can come in our bodies as we consume them. And so to combat this problem, we propose to make fluorescent crown ethers, which are essentially heterocyclic molecules composed of ether linkages that could bind to heavy metal cations and fluoresce in the presence of them. And we actually found that the synthesis of these complexes were lower compared to the ICP AES method, which is the Environmental Protection Agency standard method. And so we will be making three current ethers and modifying them with different substituents to possibly promote molecular rigidity, metal binding, and fluorescent response. And so the three current ethers we will be making are the monoaza, based off its one amine group, diaza, as it has two amine groups, and a pyridinal derivative of the diaza, which is more resonance stabilized. We'll also be doing a complex formation analysis via a fluorescence titration and jobs plot and establishing a limit of detection, which is essentially letting us know what is the minimum amount of metal needed for our current ether to fluoresce in the presence of them.
So once we finish synthesis of our molecules, we characterize them using Proton Nmr, and the two signals below illustrate that we did synthesize our molecule and that we did get close to literature results. So once we were able to do that, we moved on to our three-dimensional analysis. And so what this did is the spectrophotometer essentially excites the molecule, and then it releases a photon of light, also known as its emission. And so the spectrophotometer excites the molecule every 10 nanometers and records its emissive response. So based on this, we're able to analyze which excitation wavelength produces the highest emissive response so we can get the best possible results. And so based on this, we got an optimum excitation wavelength of 260 nanometers across our crown ethers, likely due to the addition of nibromofluorine, the same fluorophore. And so after this, we were able to do our fluorescent metal analysis. And so for this, we dissolved the divalent metals in a basic tris buffer solution, and we dissolved our crown ether in a basic tris and acetonitrile solution. And then we combined them and then sonicated them, and then we eventually recorded the fluorescence response. Um, and so for an expectation of our binding constants and fluorescent response, we do expect the pyridinal azacrown ether to have the highest fluorescence response because the resonance stabilized amine group contributes to the softness of the ligand itself and thus favors interaction of softer metals, which is the heavier metals we're trying to bind. Um, and we do predict the monoaza itself to be less effective and have a lower intensity due to the lack of the secondary heterocyclic nitrogen, which is a better and softer base. And so for our future works, we do need to continue with the fluorescence titration between our crown and the divalent metals we have, and then with an increasing metal concentration. And from this, we will also be able to understand the limit of detection and create a calibration curve based off of the metal concentration and fluorescent response. We also need to conduct a 3D analysis of our crown ether complex following binding to the metal, because metal binding can affect the excitation and emission wavelength of our molecule. And finally, we do need to continue with our jobs plot analysis, maintaining a total 40 micromolar concentration of the atoms in the solution. And from this, we'll be able to analyze the stoichiometry of the binding event if the crown and metal are binding into in a 1-to-1 ratio, or if there's some deviance going on.
And we just want to thank the ACT program and the Department of Chemistry and Biochemistry really quickly, as much of this would not have been possible without their help. If you have any questions, feel free to leave them down below. Thanks.